So current is a measure of how much charge passes a specific point in your circuit per second. So when we talk about current, we're going to be looking at charge. The symbol for charge, by the way, has the symbol Q. Capital Q is the symbol for charge. We're going to be looking at how much charge passes a point in your circuit per second. So imagine you've got a wire and you're looking at just sort of one little cross-sectional area of your wire. You're counting how much charge passes that point in 1 second. Here's an analogy for current. You might think of a current as being the amount of water in a river, but not just the amount of water sitting there in the river, right? If you just had a whole bunch of water sitting in the river, that wouldn't be a current, it wouldn't be flowing. A current is like an amount of water that's moving down the river per second. So to measure the current in a river, you'd have to sort of stand at some point in the river and look at, well, how much water is flowing past me in this point every second? And that's what current in a river would be. It's exactly the same idea in a wire. It's how much charge is passing you per second. So just some things we need to know. The symbol for current is capital I. The units are amps or amperes. So that is a capital A for amperes. But another unit, if we think about current as a charge per second, how much charge is moving per second, well, the units of charge are what's called coulombs. So it's a capital C for a coulomb. So another unit for current is a coulomb per second, right? How much charge passes per second. Then that leads us nicely to our equation. So the definition of current is that I, current, is the charge that passes a certain point in 1 second, so over some delta t that has gone by. All right, so there's one really unfortunate thing with current, which is that back in the 1700s when Franklin was looking at current, he set the direction for conventional current flow. And unfortunately, we didn't know very much about like the structure of an atom and what protons and electrons were and all that sort of thing back then. And so Franklin thought, you know, in a wire looks like this. In a wire, you've got positive charges and negative charges. And in a neutral wire, you have to have an equal number of both, right? And so if you just pick up a wire off the shelf one day, that wire is going to have a neutral charge to it. So the wire that is currently connecting, you know, my computer to the wall probably has neutral charge. Has an equal number of protons and electrons, or positive charges and negative charges. And one of those things has to be moving. So current is not just charge sitting there, current is charge that's moving. So either those electrons are all moving this way, right? Maybe they're all moving and the protons are sitting still. Or maybe all the positive charges are moving this way and maybe all the electrons are sitting still. Either way, you still have an overall neutral wire. You have the same number of protons and electrons, but you have to have some moving charge. And so it's either the positives or the negatives, or maybe it's both. Franklin thought, well, you know, it's probably the positive charges that move. That would make sense. And so that's what he set as being the convention of current flow. Turns out that that was wrong. So that's not the case at all. Now we know a little bit more about the details at a smaller level. Positive charges are protons, and protons are actually really big compared to an electron, like a lot bigger than an electron. So protons in a wire are fixed in place. They're not going anywhere. When you have a wire, your protons are in this crystal lattice and they just stay there. But the electrons are super tiny and they're able to free move nicely all around any kind of a metal or conductor, which is a wire. So actually what's happening is the electrons are moving this way and the protons are staying put. So that's what's really going on. Unfortunately, we discovered that quite a while after Franklin had set the convention for current flow, and maybe physicists were just a little bit lazy, and so basically everybody in the world uses what's called conventional current, which is the idea that positive charges, or protons, move around circuits and electrons stay still. Even though we know that's not the case, that's not what's actually happening, we pretend that positive charges move. So when we draw our circuit diagrams, we're going to be drawing things as if positive charges are moving. It's kind of weird, but we're kind of stuck with it just because it'd be a lot of work to change everything, and I guess physicists were a little bit lazy. Maybe you can be the one to make the change. But so far, we pretend the positive charges move just because Franklin made the wrong convention several hundred years ago. All right, here's one thing that is true and is really important about current. So current always flows in a closed loop. So what you want to think about current as being is like little tiny, all those little electrons that are moving, or we pretend protons are moving, but it's actually electrons. All of them, think about them as little beads on a string. So here's your wire, and maybe your wire has like a light bulb in it or whatever here. And that wire is full of little tiny electrons, right? So there's, oops, there's an electron, there's an electron, there's an electron. And there's electrons inside the light too, right? There's electrons in here. Electron, 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 electron. I'm not great at drawing these, but here we are, lots of little electrons. Think about those electrons as little tiny beads on a string. And so when you turn on the light bulb, when you flick that switch, what you're doing is you're allowing a push to happen at this end. So not anywhere near the light bulb necessarily, sorry for that. But you're pushing on this electron over here. And if you push on this electron, well, he's going to push on the next one. That electron will push on the next one. He'll push on the next one, and he'll push on the next one, and eventually they'll push on the electrons that are actually inside the light bulb and cause them to move through the light bulb. And that's what turns the light bulb on. So as soon as you push over here, you're going to make all of the electrons in this circuit move. But now imagine what would happen if you cut the circuit right there. So if the wire just stopped here and there was nowhere for this electron to go, well, all of those pushes would happen all the way down, but then this electron is stopped. He's up against a wall. He can't just go anywhere. So you can push as hard as you want. The electrons aren't going to move through the light bulb. If there's a break in the circuit anywhere, even after the bulb, the electrons have nowhere to go. And so that means that no current will flow. And your light won't turn on. So the circuit won't work at all. So if you want your circuit to work, you have to have a closed loop. So a closed loop will look like this. This has to loop right back here. And this is all full of little electrons that can now push on each other. So when I push on this first electron, all of these electrons can flow through, and these electrons just like keep going right through the pushing device. And what that pushing device is some sort of a voltage. So maybe it's a battery, or maybe it's your wall outlet, but it's something that has a potential difference or voltage, and we'll talk about that more soon. You need to have a closed loop in order for the electrons to have somewhere to go for current to actually flow. That's actually why all of your electrical devices have two prongs on them. So when you plug something in, so say you plug in your hair dryer, it kind of looks like there's just one wire going to the wall, right? But there's not. There's actually two. There's one that's taking the electricity, the little electrons are coming from the wall, coming up to your hair dryer, going through the hair dryer, heating it up, and then that's what makes your hair warm. And then going back, and there's actually another wire inside this part, and that one comes out the other prong back into the wall. And that gives you that closed loop. If you cut off one of the prongs on your hairdryer, it won't work, right? Because that's like breaking your circuit right over here. You put a break in that circuit there, none of the electrons can flow anywhere, no matter how hard the wall is pushing. If one of the prongs is broken off, you can't be sending electricity through your hairdryer, so it won't work at all. Just as an aside, you'll notice some devices, like larger devices, maybe like your dryer, probably has 3 prongs on it. The third prong has nothing to do with this closed loop. The third prong is actually just about a ground. It's just to keep you safe. So anytime you're using a device that pulls a lot of current, like a dryer, then it's going to build up a little bit of charge on the surface of the dryer, and things can go wrong there, and you can end up with a charged up dryer, which would not be great because then you go to take your clothes out of the dryer and you get a really big shock. So the third prong is just to funnel any extra electrons that happen to accumulate on the outside of the dryer, funnel them away into the ground, essentially, so just get rid of them, so that they don't shock you if you ever touch the dryer. So that's all that third prong is for. You don't need it for small devices. but for really big devices that draw a lot of current, then it's helpful. All right, let's do a quick example problem here. So let's say you have 35.2 microcoulombs. So as soon as you see that capital C as a unit, that's a coulomb. That tells you we have a charge, and the symbol for charge is capital Q. So the charge this light bulb is feeling is 35.2 microcoulombs. Now that's not an SI unit. I need to convert the micro into what it is. And if you remember from our very first unit, it's a long time ago, micro is times 10 to the negative 6. So get that into nice SI units. That micro will be 10 to the negative 6. So that's Q, your charge. And we're told that it takes 1 minute for this charge to pass through the bulb. So that means delta T is 1 minute, also not an SI unit. It's going to be 60 seconds. We convert that. Okay, what is the current? Current is just Q over delta T. I don't have to do any rearranging here. This is already arranged for I, which is current, so that's really nice. You can just plug in your numbers. 35.2 times 10 to the negative 6 divided by 60. And let's see what that is. You would get 5.87 times 10 to the negative 7, and the units of current are amps. Sig figs, it's a little bit awkward here. I just use the word 1, which is extremely vague for sig figs, so that doesn't really tell me anything at all. So we'll go with this for our sig figs. There's 3 there, so we can use 3 in our answer here.